February 4th, 1850. Work was just starting at the Hay Street printing press in New York City. But in the basement, temperatures inside their coal-fired boiler were reaching dangerous levels. A force of nature was struggling to break free. At 7:45, a huge explosion tore the building apart. Dozens were killed and many more injured. The boiler had overheated and exploded. Disasters like this were happening daily during the Industrial Revolution. We'd begun to harness energy, but we were struggling to control it with any precision. It's perhaps not surprising. After all, what is energy? Such an intangible thing to measure and understand. In this series, I've been exploring how we use measurement to quantify every aspect of our world, creating a system of 7 fundamental units which have become the building blocks of modern science. From time and distance to temperature and mass, I want to understand how we've imposed order on the universe with these basic units of measurement, and how through history each step forward in precision has unleashed a technological revolution. This program is all about energy, a difficult and dangerous force that comes in many forms. The quest to describe this mysterious power with a few simple units has been a challenge for the greatest of minds. But it has also had the most profound consequences for the way we live. This is the story of light, heat, and electricity. Hundreds of kilometers above our heads, a fleet of satellites watch over the Earth. What they can do seems almost magical, beyond belief. They can measure the thickness of sea ice with millimeter accuracy, measure the temperature of our oceans or the subsidence of your house. And all of this is only possible because of our precise ability to measure energy. Harnessing the power of light, heat, and electricity has transformed our lives in ways no one could have predicted. But how do we learn to measure energy with such precision? Until the late 17th century, no one really understood anything about energy. Heat was considered a strange, invisible fluid. Electricity, a frightening and incomprehensible force of nature. And light, something God-given that shone down from the heavens and ripened our crops. It took the brilliance of Isaac Newton to revolutionize the understanding of energy, making the intangible tangible. And it started with light. The year was 1665, and as the plague took hold of Britain, Newton fled his rooms at the University of Cambridge for the safety of his country retreat. He came here to Woolsthorpe Manor in Lincolnshire, and it's here that it's thought that he came up with a series of experiments that would change the way we think about light forever. At the time of Newton's experiments, it was well known that if you pass light through a prism like this, then a spectrum of colour is produced. But what most people thought was that somehow the prism was colouring the light. But Newton thought differently. He wrote in a letter to the Royal Society, "Having darkened my chamber, I made a small hole in my window shuts to let in a convenient quantity of the sun's light. I placed my prism at his entrance." Now, to prove that it isn't the prism that's colouring the light, Newton had a brilliant idea. What he did was to isolate one of the colours, and he did that using a screen. I'm going to pick out the green. Now, if it was the prism that was colouring the light, if I put a second prism in front of this green, it should change the colour. But when Newton did that, what he saw was the same green colour on the wall. It wasn't the prism that was colouring the light. Newton had proved that it was the sunlight that was made up of all of these different colours. He'd unearthed the secrets behind the visible light spectrum. His account continued. Light is a confused aggregate of rays, imbued with all sorts of colours. The blue flame of brimstone, the yellow flame of a candle, and the various colours of the fixed stars. Light was now something that could be analysed. Solving its mysteries would allow light to be manipulated, and most importantly of all, measured. Hypersensitive and extremely secretive, for years Newton didn't mention the experiment to anyone. But finally, in 1672, he submitted his first formal paper about the experiment to the Royal Society. When it was read to the fellows, it was met both with singular attention and uncommon applause. This experiment sowed the seeds for the age of enlightenment, the age of science. When Newton discovered the visible light spectrum, what he didn't realise was that there was also light that he couldn't see. And we call it infrared. Over 100 years after Newton's discovery, astronomer William Herschel stumbled upon these invisible rays. Experimenting with the visible light spectrum, Herschel began taking the temperature of all the different colours. To his astonishment, when he placed the thermometer beyond the red, the mercury began to rise. So I got a much more sensitive thermometer here called a thermocouple, and you can see on the screen, which is measuring the temperature, there's a sudden surge out beyond the red. There we go. There's the spike. Wow. Herschel called these invisible rays calorific rays, but we know them today as infrared. And in fact, all the waves, infrared, radio waves, X-rays, microwaves, gamma rays, they're all, like visible light, certain forms of electromagnetic radiation. And all of this electromagnetic radiation are made up of photons of light, of different wavelengths, some which we can see and some which we can't. And it's the measurement of these invisible rays which is at the heart of 21st century measurement. If light is made up of wavelengths of photons, what is heat? For millennia, this question remained a mystery. But its nature can best be seen using a heat-sensitive camera. So if I take this piece of wood and hit it with a hammer, then the infrared camera is picking up a change in temperature. It's getting hotter. So the mechanical energy of the hammer is causing an increase in heat. to understand what is happening in the wood, I've come to meet heat expert Michael de Podesta.
Heat is the motion of molecules. Everything around you right now, inside it, the atoms and molecules are moving. They're moving very, very fast. Each of those fat globules is being bombarded by the atoms around it.
Okay, so I can't see the atoms, but what I'm seeing is the effect that those atoms and the heat, which is the movements of those atoms, has on the globules of fat.
Exactly so. Heat is a type of energy. It's the energy that's tied up in the motion of the particles. But temperature is a measure of their speed.
Right. So actually when I touch something and I'm actually detecting how hot it is, what I'm really detecting is how fast the molecules are moving on the surface.
That is exactly what you're detecting. It's astonishing.
To get to this molecular understanding of temperature, we first had to go through hundreds of years of experimentation and invention. And it all started in Renaissance Italy in the 16th century.
Using touch, or seeing how the colour of something changes as you heat it up, was about the only way we knew how to measure temperature for thousands of years. An accurate temperature measurement remained elusive until a breakthrough was made here in Italy towards the end of the 16th century.
And that moment came from the father of modern physics, Galileo Galilei. He revolutionized so many different areas: astronomy, physics, mechanics, and my own subject of mathematics.
But for me, the really big surprise is that Galileo was one of the first to come up with a way of measuring temperature.
At the time, he was reading a recently translated text by an ancient Greek mathematician and engineer, Hero of Alexandria. And it's thought that Hero's ideas inspired Galileo to look at temperature. Galileo invented what was then called the thermoscope. It was wildly inaccurate, but it was the world's first thermometer. A friend observed Galileo's groundbreaking experiment. He took a small glass flask, about as large as a small hen's egg, with a neck about 2 spans long and as fine as a wheat straw, and warmed the flask well in his hand. When he took away the heat of his hands from the flask, the water at once began to rise in the neck.
What Galileo was exploiting here was the fact that if you heat something up, like air, it expands, so the level of the water goes down. And if I take my hands off and let the flask cool down, then suddenly the level starts to go up again. So suddenly we had the first way of measuring the temperature instead of using our hands or our eyes.
Intrigued by the practical possibilities of temperature measurement, esteemed physician Santorio Santorio began making his own thermoscopes. He'd noticed that when his patients were feverish, they felt hotter than usual, and he wanted a way to prove it. He gave the thermoscope a scale, and for the first time recorded the temperature of a patient's mouth. But because it was open-ended, it was highly inaccurate, the results varying according to local air pressure.
Over the next few years, Florence became a hotbed for thermometer experimentation.
In 1657, the Medici family set up and funded the Accademia del Cimento, known as the Academy of Experimentation. Their motto was, proving and proving again. and temperature measurement was all the rage. It was a real fusion of art and science, using the skills of some of the finest glassblowers in the world. Thermometers became increasingly accurate. Water was replaced with alcohol, and the stems became sealed. Designer Sagredo built circular thermometers with 360 divisions, an idea he borrowed from the ancient Babylonians, who were the first to divide circles into degrees. It's why today we measure temperature in degrees. Having a thermometer became the height of fashion for any thinking man. The intangible had become tangible. By the end of the 18th century, we didn't really understand what temperature was, but we did have a means of measuring it. As for light, the opposite was true. We understood what it was, but we couldn't measure it. However, the study of the other great form of energy, electricity, was in its infancy. For thousands of years, lightning and strange tales of torpedo rays were the only manifestations of this awesome force that we knew about. Striking fear into our hearts, all we could do was observe its blinding light and its searing heat.
Before the 18th century, we had little idea what electricity was. We could only puzzle over the effects of static electricity, marvel at the destructive power of lightning. So how did we come to exploit and measure it so precisely? To answer that question, we have to go back 300 years to a world that was dark, cold and quiet. When the working day was determined by when the sun set, letters were delivered by horseback, and electricity was just a spectacle performed by showmen who called themselves electricians.
But this was also a time when people were becoming increasingly inquisitive about their world.
The 18th century was a remarkable period in the history of measurement. This was the age of the Enlightenment, when scientists were looking at the world around them with a keen eye, trying to find rational explanations for the phenomenon that they observed.
And the strange force of electricity was coming under scrutiny.
The breakthrough was made here in Pavia in northern Italy, and it was made by a charismatic and brilliant young scientist called Alessandro Volta, who became obsessed with the seemingly magical power of electricity. In a state of deep emotional distress after a torrid love affair with a beautiful opera singer called Mariana, the lovesick Volta threw himself into the investigation of animal electricity.
And the animal he studied was the torpedo ray, a fish capable of electrocuting its prey.
What Volta was intrigued by was, what was it inside the torpedo ray that was causing this electrical shock? When he looked inside its anatomy, what he found was a column of cells that seemed to be responsible for the shock. So this is what he tried to copy.
Now, Volta must have played around with many different ideas, trying things out, nothing worked, until suddenly he had a breakthrough.
His lead came from the work of Luigi Galvani. Attaching copper and iron wires to a dead frog, Galvani discovered that he could make its legs twitch. He believed he'd found a strange new force inside the frog. Volta's brilliance was realizing the phenomena was actually down to Galvani's use of two different metals. Inspired, he set about recreating the torpedo ray's cell column using alternating types of metal.
First of all, he took a copper metal plate, put that one down the bottom of the pile, and then on top of that he put a metal plate made out of zinc. And then the next ingredient was a piece of card soaked in a weak acid solution. And then that gets put on top of the zinc. So that's our first cell. And then he's going to make copies of these cells, build up this kind of pile, a little bit like in the torpedo ray. Another piece of acid. So that goes on there. Now, to test his idea, what he did was to attach a wire to the bottom copper plate, another wire to the top zinc plate, and then what he hoped was he'd get an electrical shock if he joined these two together. And to really test it, what he did was to place the two ends of the wire on his tongue to actually feel the shock. So hopefully I haven't made this too powerful. Let's try this out. Yeah, it's quite gentle, but there is definitely the taste of the fizz of electricity. And the more cells I put on top of this, the bigger the current. Now, to prove that I'm not just acting, I've got a little light bulb here. So if I attach this to one end of the wire, and then to the other, there we go. The light lights up. But what's amazing about this is it's not just a spark of static electricity or the shock of the ray. This is a gentle, continuous stream of electricity. This was the first time this had ever been done. And this is what really gave birth to the modern battery.
In Voltaire's typical self-confident and flamboyant way, he toured the lecture halls, showing off his great invention. Other scientists latched on to the discovery, using the cells in their own experiments. It would take hundreds of years before we fully understood electricity, but Voltaire had begun to unlock its secrets. Electricity, light and heat were no longer supernatural forces, but tangible forms of energy that were attracting the greatest minds in science to their study. And these scientists soon realized better measurement would hold the key to harnessing their immense power. By the time Voltaire was creating the world's first continuous electrical current, thermometers had already been around for 200 years, but readings varied depending on whose model you used. It took Polish-born scientist Daniel Fahrenheit to make the first big leap in standardizing temperature measurement. He chose mercury, as it expands more uniformly than other liquids, and is liquid over a wide temperature range. But his real innovation was to introduce two reliable and reproducible fixed temperature points, so a scale could be calibrated. At the low end, he chose the melting point of pure ice at 32 degrees, and the upper end, 96, the temperature of human blood. This later changed to the more practical boiling point of water at 212. And as Celsius simplified things, choosing a 100-degree scale based on the boiling and freezing points of water. His brilliance was to calibrate his thermometers to standard atmospheric pressure, making them accurate whatever the weather. Both scales are still used today, but it took the Industrial Revolution to show up their limitations. As the demands for ever greater accuracy and range grew, the Celsius and Fahrenheit thermometers were simply not up to the job in the fast-evolving world of heavy industry. By the end of the 19th century, steam engines like this Watt engine were really driving the Industrial Revolution. They were pumping down mines, in distilleries, controlling the machines in factories across the country.
This extraordinary engine at Papplewick would be pumping over 1.5 million gallons of water a day for the citizens of Nottingham.
The 6 huge furnaces would use 100 tons of coal a week, shoveled by a team of 14 men, working back-breaking shifts around the clock.
The temperature inside this furnace is getting to over 1,000 degrees centigrade. That's heating water at the back, which turns into steam, which using some valves drives the pumps of the Watt engine. Now the thing is, when water turns into steam, the volume changes by a factor of 1,600, and that's where all the power comes from. Now the pressure depends on the temperature inside this furnace. Get that temperature wrong, and the whole place blows sky high.
By the second half of the 19th century, boilers were exploding at a rate of almost 1 every 4 days in America alone. One of the worst incidents was later called the Titanic of the Mississippi. The American Civil War had just finished, and the steamship Sultana, packed with newly released Union prisoners of war, was returning home. At 2 a.m. on April the 27th, 1865, her boilers exploded, tearing the ship apart. Over 1,700 lost their lives in what remains one of America's worst maritime disasters. Steam power was changing our world, but at a high cost. Thermometers simply wouldn't work at these high temperatures. The glass would break. And the Fahrenheit and Celsius scales themselves were far too inaccurate at recording temperatures so much higher than the boiling and freezing points that they were based on. A new means of measuring high temperatures was urgently needed, and the answer ultimately came from an unlikely source: electricity.
The breakthrough came in 1820 when a German scientist, Thomas Johann Seebeck, realised that if he took 2 wires of different metals and wound them round each other and put the 2 wires inside the furnace, then took a compass and put it over the wires, he discovered that the needle of the compass moved. There was a magnetic field being caused by this wire. The difference in temperature between the end inside the furnace and this end here is causing a difference in voltage potential, which is creating an electrical current running through this. The electrical current causes the magnetic field, and that's what's being picked up when I put the compass over the top of this.
This simple observation is what led to the creation of a device called a thermocouple.
In fact, a modern-day thermocouple can actually measure this voltage difference. I can record the heart of the furnace that it's going up 900 degrees. Look, it just topped over 1,000 there. And for me, the amazing thing is that we're using the measurement of electricity to actually find out what the temperature is inside this furnace.
But before we could fully harness heat's power, we needed to understand what heat really was. In the 18th century, a popular theory among scientists was that heat was an invisible liquid that flowed in hot substances. It took keen amateur scientist James Prescott Joule in 1840 to start to unlock its mysteries.
And it begins in rather an unlikely place, a brewery.
Rather fond of beer, Joule realised that accurate temperature measurement was crucial to making a good pint in the family brewery.
He became so good at measuring temperature that he claimed you could measure it to an accuracy of 1/200th of a degree Fahrenheit. But he also worked out something else, something that was crucial for scientists to understand. He devised a simple experiment that had an extraordinary result.
Placing a paddle in a tank of water and turning it using the energy of a falling weight, he found that the temperature of the water went up. He also found that if the weight fell from even higher, the water got even warmer. Joule had discovered mechanical energy could be transferred into heat. It was a huge breakthrough. Heat wasn't an invisible fluid, but a form of energy. But at the time, the scientific community largely shunned his findings, refusing to believe this middle-class brewer could have anything meaningful to contribute to science. It took a chance meeting for Joule to be taken seriously. On honeymoon in the French Alps, and still obsessed with proving his theories on heat, Joule spent his time not with his wife, but at waterfalls, measuring the difference in water temperature between the top and the bottom. And it was here that he bumped into the world-renowned scientist, Lord Kelvin. Their friendship would revolutionize our understanding of heat. And inspired by the work of Joule, Lord Kelvin set about devising a new temperature scale. No longer would temperature measurement be based on the boiling and freezing points of water, but on the very nature of heat itself, energy. Performing hundreds of gas experiments, Kelvin's goal was to find the coldest temperature in the universe, and to use this as the base for his new scale. This is liquid helium, and all this movement is caused by the molecules firing around inside it. But as the temperature drops, something strange starts to happen. The molecules slow right down until they virtually stop moving. The helium is close to a theoretical temperature called absolute zero. Kelvin calculated this to be minus 273 degrees Celsius, a temperature where molecules no longer move. There is no energy, and therefore no heat. The inside of this flask is now one of the coldest places in the universe. Using absolute zero as the lower point of the scale, Kelvin had tied its base to the nature of heat. Yet to make the scale practical, what was needed was a fixed point higher up. Kelvin died before his theories were put into practice. But the scientists that followed in his footsteps chose a strange phenomena called the triple point, where a substance can exist simultaneously as a gas, liquid, and a solid.
Now, the reason measurement scientists like this triple point so much is that it happens at a very precise temperature. So at this point we see the nitrogen in liquid and gas form, and we're going to reduce the pressure.
As the pressure drops, so does the temperature, and the nitrogen begins to solidify.
And we should be able to get, there we go. We've now captured the nitrogen in both liquid, gaseous and solid form. You can see this solid, kind of like nitrogen ice sitting on the top. And the gas is bubbling underneath, pushing the solid up, and the liquid below that.
The old Fahrenheit and Celsius scales were fixed to the boiling and freezing points of water, which can vary enormously. The beauty of triple points is that they never vary by more than a few millionths of a degree.
Now, with this idea of a theoretical absolute zero, and these triple points corresponding to different substances, nitrogen, water, finally the world had a precise scale to measure temperature.
Half a century after his death, the Kelvin was adopted as the international unit of temperature measurement and tied to a fixed point more accurate than Celsius and Fahrenheit could ever have imagined, the triple point of water. With it, incredible feats of engineering were now possible. From forging metals to growing crystals, the world finally had a temperature scale it could trust. Like heat, the story of electricity also took a giant leap forward during the Industrial Revolution. It was French maths prodigy and physicist André-Marie Ampère who was to make the next real breakthrough. Intrigued with Ørsted's discoveries, he decided to further investigate the relationship between electricity and magnetism.
Using apparatus very similar to this, he discovered that if he passed an electrical current between two parallel wires, it created a magnetic attraction between them. Now, I beefed up the experiment a little bit by using these coils of wire, but if I turn on the electrical current, the coils are then attracted to each other. And the key thing for us is that greater the electrical current, so if I beef that up a bit, the greater the magnetic force between them.
Ampère had found a new way to measure electricity. By measuring the strength of the magnetic force, he was able to build a machine to measure current, called a galvanometer, named in honor of electrical pioneer Luigi Galvani. And there was a practical use to all this. Ampère's work was about to pave the way for modern communication. The first telegraph systems were basically a wire with a galvanometer stuck at each end. They worked by sending pulses of current down a wire, which then deflected these needles. Messages could now be sent at a speed of about 6 words a minute. But it took a grisly murder for this newfangled invention to be taken seriously. In 1845, John Tawell poisoned his lover, Sarah Hart, with a deadly drink of prussic acid. Fleeing the scene, he jumped on a train to London. The alarm was raised, and a telegraph message sent to Paddington Station. A murder has just been committed at Salt Hill, and the suspected murderer was seen to take a first-class ticket to London by the train which left Slough at 7:42 p.m. He is in the garb of a Quaker. The message took 10 minutes to get to London. The train took 50. On his arrival, Tawell was met and tailed by a London bobby. News of his spectacular arrest made every paper in the country. The power of electrical communication was clear for all to see. Soon telegraph lines were being laid across the world. A revolution in global communications was underway. But with no international system of measuring electricity, there were serious problems. If too much current was pushed down the line, the wires caught fire. Too little, and the message never got through. With lots of competing and different units of electrical measurement in use, standardization was urgently needed. And in 1881, on the site of the Grand Palais here in Paris, that dream would become a reality.
It was at the first Congress of Electricians, attended by 250 people from 28 different countries, that the ampere, the volt, the ohm and the farad were finally defined.
Ultimately, it would be the ampere that will become the international unit for electricity.
Finally, the world had a standard for accurately measuring electricity.
As the brains of the electrical world met behind closed doors, the French public were being treated to the greatest exhibition of electricity ever seen.
All along the capital's tree-lined avenues and in the exhibition halls, the latest electrical lighting, trams, telephones, generating systems, signalling devices would have been gathered for the Congress and the whole world to see. It must have been an extraordinary sight. In fact, onlookers described it as a great blaze of splendour. It really marked the spirit of the age, the spirit of innovation and invention.
But it was a young American engineer and entrepreneur who stole the show that year. His name was Thomas Edison. In two enormous rooms filled with crystal chandeliers and hundreds upon hundreds of lights, the crowds were dazzled and amazed. But the invention that caught everyone's attention was his giant electrical generator, capable of lighting 1,200 lamps. With it were plans for the first complete electrical supply system. A system that would bring together the power of heat, electricity and light for the very first time. At its heart would be a steam-driven power station that would supply enough electricity to light over 100 businesses and private houses. Edison was about to light up our world.
Six months later, Edison's dream would become a reality. On the 4th of September 1882, Edison switched on his Pearl Street power station. An electrical current started flowing to 59 customers in Lower Manhattan, powering 400 lamps.
The newspapers reported how, in a twinkling, the area bounded by Spruce, Wall, Nassau and Pearl Streets was in a glow. It marked the dawn of the electrical age.
The world would never be quite the same again. Electricity had arrived.
And even Edison must have been surprised by its popularity.
Within 2 years, demand for Pearl Street electricity had rocketed tenfold. Electricity soon became a household commodity, like buying a load of coal or a box of matches, at least if you could afford it. The next great challenge was measuring how much people were using.
But the galvanometer and the units defined in Paris couldn't do this. Edison could have charged his customers based on the number of lamps they had. But soon he realised this was not a profitable way to do business. What he needed was a way to measure current usage over time. And his solution was to use the principles of electroplating. Edison's first electricity meter basically consisted of a glass jar with 2 copper plates suspended in a copper sulfate solution. Now, as I pass electricity through the cell, then what happens is that atoms transfer from the solution onto the plate, making the plate heavier. Now, the key point here is that the total mass of copper deposited on the plate is directly proportional to the total current running through the system. So now if I switch off the electricity and we take the plate out, you can see here the copper that's been deposited.
Now, the amazing thing for me is that instead of measuring this rather elusive property of electricity, we're actually just measuring a change in weight. Finally, Edison had a way to charge his customers for the amount of electricity they'd use. He'd send out one of his employees to visit the cells. They'd take out the plates, measure the change in weight, and the customers would be billed accordingly. Now, it wasn't a brilliant system, but at least it was a system for measuring the amount of electricity that had been used.
While the measurement of heat and electricity was making great advances in the industrial era, the quest to measure light had been all but forgotten. It took the emergence of streetlights to change all this. Before Edison lit up our world using electricity, the very first lamps were powered by gas. It was the beginning of the 19th century. Theft was on the rise, and murder was commonplace. There was a desperate need for safer streets. And that came with the installation of the first public gas lights here in central London in 1807.
Demand for this newfangled gas lighting soared, and soon unscrupulous companies were cashing in, selling low-quality gas at high-quality prices.
The outrage that ensued forced the government to introduce a new measure for light intensity.
It was called candle power, and it was based on the brightness of a special candle made out of beeswax and the naturally occurring oil taken from the head of a sperm whale. The spermaceti candle.
The new unit was to be the light produced by one spermaceti candle, weighing 1/6 of a pound and burning at a rate of 120 grains per hour.
It was the world's first attempt to try and produce a standard measure of light intensity, but it was still very arbitrary. Light inspectors would go out, hold up greasy bits of paper, trying to compare the brightness of light coming from gas lamps to those of a candle. Now, it had a fundamental problem that still haunts the measurement of light intensity to this day. It depends entirely on our own perception of light. Now, this is the light produced by 100 candles. In a moment, I'm going to extinguish 50 of them. The problem is that the pupil in my eye expands and contracts to control the amount of light entering them, which means that when I extinguish half of them, it isn't going to look half as bright. Now, although the camera is recording a lower light condition, to my human eye, although I've got half as many candles, this looks as bright as it did before.
It took a remarkable series of experiments in the 1920s to solve the riddle of human light perception. In an international study, 200 people aged 18 to 60 underwent a series of tests to find out what colour wavelengths we see best, and how our eyes combine these different colours to perceive brightness. Their work would lead to the creation of the candela, the unit we use to measure light today. Here at the National Physical Laboratory, Dr. Nigel Fox can show me how unreliable my eyes are as a means of measurement.
Yes, that's good. So let's measure. So it looks a bit like a 70s disco here, right?
Yes. Well, we can't quite reproduce the experiment of the 1920s. The equipment has all disappeared, but what we've tried to do is to simulate the effect of that experiment here. So, Marcus, which of those lights looks the brightest to you?
Well, I would say that the green one seems to be a lot brighter than the red and the blue. The red and the blue, maybe blue next and then the red third. But yeah, the green certainly seems the brightest.
Well, would it surprise you if I said the green is less than all of the others?
Oh, really? Less intense?
That's right.
Yeah, you're not tricking me.
No, this is...
So what's this recording then?
This instrument is measuring the actual radiometric power that is coming from those different light sources.
And as the instruments prove, my eyes really are deceiving me.
That's extraordinary. The red is actually much more powerful than the green, yet my eye is seeing the green as more luminous.
Exactly.
The 1920s tests revealed not only that our eyes were much more sensitive to yellowish-green light, but that our age and sex also affect how we perceive the brightness of light. Compiling their results, the scientists came up with an average human perception of brightness. It's roughly equivalent to how a woman in her late 20s sees light. To this day, the definition of the candela remains locked to these findings.
I can understand the need for the candela. I mean, having a unit of measurement which measures how the human eye sees light is clearly useful. I mean, take this traffic light that's coming up. I want to know that it's bright enough that I'm going to see it, but not so bright that it's going to dazzle me. The same applies to the car headlamps, street lamps, lights in our home. The list is endless. Because it's based on human perception, there's something rather odd about the candela as a unit. I mean, it's kind of the black sheep of the measurement family.
And the candela's days are numbered. Today, scientists are trying to base all measurement on the fundamental, unchanging laws of the universe. We've done it for the meter, basing it on the speed of light, and the second on the movement of electrons inside an atom. Now the goal is to do the same for heat, electricity, and light. Today, just as during the Industrial Revolution, our ability to measure these energy units is failing to keep up with the demands of industry. Here at Rolls-Royce, measuring and harnessing heat at temperatures higher than 2000 degrees Kelvin will help deliver more fuel-efficient and powerful jet engines. Accurately measuring very high temperatures is a huge technical challenge.
This is the high-pressure turbine blade. This is the first rotating component that the gas stream would encounter, coming down from the combustor.
So whereabouts is that in here? I mean,
so it's just
downstream of the...
yes.
Right, so this is exposed to extreme temperatures.
It is indeed, and temperatures above its melting point.
Above its melting point?
Above its melting point.
So this would actually... should be melting then, but okay, so how do you make sure it doesn't melt?
We actually have to heavily cool them, so you can see some of the features that do that, the holes on the surface, there are passageways inside of the blade. Finished items would have a coating on them as well, a thermal barrier coating, a ceramic layer, which also takes a lot of the heat away.
Despite state-of-the-art thermocouples, computer modelling and thermal paints on the turbine blades, the experts here can only achieve an accuracy of about 4 degrees Kelvin. Better accuracy isn't just a technical problem. The Kelvin scale itself loses accuracy the higher temperatures get.
Today, new technologies are pushing temperature measurement to the absolute limit, such that a new standard is critically needed. Here at the NPL Heat Lab, they think they might be close to cracking it.
Michael Di Podesta has built the most accurate thermometer in the world, an acoustic gas thermometer.
It's the culmination of a 150-year story that began with Kelvin himself. What we're doing is we're determining temperatures in terms of the speed with which molecules are moving. What we measure is the speed of sound through argon gas trapped in this container down here.
It seems extraordinary to be using sound in a way to be measuring temperature.
Well, if you think about a sound wave, momentarily gas is compressed and that heats up the gas, and the gas then springs back and you're turning that thermal energy, the motion of the microscopic motion of the molecules, back into mechanical energy. So sound is directly linked to temperature. So what we measure is the speed of sound, and what we can infer very, very directly is the speed of the molecule.
If it's successful, the acoustic gas thermometer will be as revolutionary for the measurement of heat as the atomic clock was for time. Just as Kelvin dreamt, it will create an absolute system based on one of the fundamental constants of the universe, the Boltzmann constant, a magical number which relates the movement of molecules to temperature.
When that happens, temperature will join the meter and the second in being tied to a universal constant of nature. And with it will come incredible precision. With devices capable of measuring accurately at temperatures hotter than the surface of the sun. It will give us greater control of heat, making engines more efficient and economical. Incredibly, in a lab just down the corridor from the acoustic thermometer, another breakthrough is underway. Here, J.T. Janssen and his team are revolutionizing the measurement of electricity. And their work can be traced back to Volta's battery experiment. We now know if you break something down into its building blocks, atoms, you'll find a positively charged nucleus orbited by negatively charged electrons. Metals like the copper and zinc used by Volta have electrons that readily detach from their nuclei. It is these loose moving electrons that enable electricity to flow, forming a current. Using some of the strongest magnets on the planet and temperatures close to absolute zero, JT's team are controlling the movement of single electrons and counting them as they pass through their experiment one at a time.
We've been working on this experiment for about 10 years now, and it's all related to trying to redefine the ampere, the units for electrical currents, in terms of a fundamental constant of nature. And in this case, that's the charge of an individual electron. And now we're at the level where we can control 1 billion electrons per second, and we're only missing a few of those.
JT's experiment will redefine our measure of electrical current using these individual electrons. They are fundamental particles, the same throughout the universe. For scientists, this is the goal: tying measurement to the unchanging laws of physics. And their work won't just impact on the world of measurement. Controlling the flow of single electrons is key to developing quantum computers. This next generation of technology will produce computers capable of calculations that are vastly beyond what is currently possible. They could simulate the human brain, model climate change in real time, and data storage using electrons would mean virtually limitless capacity. As we delve deeper inside the fabric of our universe, into the quantum world of subatomic particles, measurement is undergoing a fundamental and exciting change. we are now using the very building blocks of matter to help us measure the world around us. Even the black sheep of the measurement family, the candela, could soon be redefined, tied to the flow of photons of light. What started with our senses and crude guesswork is now getting down to the smallest building blocks of the universe, as our human urge for ever greater precision drives us forward. Measurement has changed the course of science and civilization. Now, as the quantum age approaches, our world is set to change once more.
But this is all part of a story which started thousands of years ago, when our ancestors began to measure time, length and weight. They were trying to understand the environment around them, to measure it, and ultimately to manipulate it. But isn't that really what's still driving us today? Because measurement is the key to understanding our place in the universe.
Solving its mysteries would allow light to be manipulated, and most importantly of all, measured.
Hypersensitive and extremely secretive. For years, Newton didn't mention the experiment to anyone. But finally, in 1672, he submitted his first formal paper about the experiment to the Royal Society. When it was read to the fellows, it was met both with singular attention and uncommon applause.
This experiment sowed the seeds for the age of enlightenment, the age of science. When Newton discovered the visible light spectrum, what he didn't realise was that there was also light that he couldn't see. And we call it infrared. Over 100 years after Newton's discovery, astronomer William Herschel stumbled upon these invisible rays. Experimenting with the visible light spectrum, Herschel began taking the temperature of all the different colours. To his astonishment, when he placed the thermometer beyond the red, the mercury began to rise.
So I've got a much more sensitive thermometer here called a thermocouple, and you can see on the screen, which is measuring the temperature, there's a sudden surge out beyond the red. There we go.
Until the late 17th century, no one really understood anything about energy. Heat was considered a strange, invisible fluid. Electricity, a frightening and incomprehensible force of nature. And light, something God-given that shone down from the heavens and ripened our crops. It took the brilliance of Isaac Newton to revolutionize the understanding of energy, making the intangible tangible. And it started with light.
The year was 1665, and as the plague took hold of Britain, Newton fled his rooms at the University of Cambridge for the safety of his country retreat. He came here to Woolsthorpe Manor in Lincolnshire, and it's here that it's thought that he came up with a series of experiments that would change the way we think about light forever. At the time of Newton's experiments, it was well known that if you pass light through a prism like this, then a spectrum of colour is produced. But what most people thought was that somehow the prism was colouring the light. But Newton thought differently.
He wrote in a letter to the Royal Society, "Having darkened my chamber, I made a small hole in my window shuts to let in a convenient quantity of the sun's light. I placed my prism at his entrance."
Now, to prove that it isn't the prism that's colouring the light, Newton had a brilliant idea. What he did was to isolate one of the colours, and he did that using a screen. I'm going to pick out the green. Now, if it was the prism that was colouring the light, if I put a second prism in front of this green, it should change the colour. But when Newton did that, what he saw was the same green colour on the wall. It wasn't the prism that was colouring the light. Newton had proved that it was the sunlight that was made up of all of these different colours. He'd unearthed the secrets behind the visible light spectrum.
His account continued. Light is a confused aggregate of rays, imbued with all sorts of colours. The blue flame of brimstone, the yellow flame of a candle, and the various colours of the fixed stars. Light was now something that could be analysed. February 4th, 1850. Work was just starting at the Hay Street printing press in New York City. But in the basement, temperatures inside their coal-fired boiler were reaching dangerous levels. A force of nature was struggling to break free. At 7:45, a huge explosion tore the building apart. Dozens were killed and many more injured. The boiler had overheated and exploded. Disasters like this were happening daily during the Industrial Revolution. We'd begun to harness energy, but we were struggling to control it with any precision. It's perhaps not surprising. After all, what is energy? Such an intangible thing to measure and understand. In this series, I've been exploring how we use measurement to quantify every aspect of our world, creating a system of 7 fundamental units which have become the building blocks of modern science. From time and distance to temperature and mass, I want to understand how we've imposed order on the universe with these basic units of measurement, and how through history each step forward in precision has unleashed a technological revolution. This program is all about energy, a difficult and dangerous force that comes in many forms. The quest to describe this mysterious power with a few simple units has been a challenge for the greatest of minds. But it has also had the most profound consequences for the way we live.
This is the story of light, heat, and electricity.
Hundreds of kilometers above our heads, a fleet of satellites watch over the Earth. What they can do seems almost magical, beyond belief. They can measure the thickness of sea ice with millimeter accuracy. measure the temperature of our oceans or the subsidence of your house. And all of this is only possible because of our precise ability to measure energy. Harnessing the power of light, heat, and electricity has transformed our lives in ways no one could have predicted. But how do we learn to measure energy with such precision?